welcome everyone. Okay, let me get my screen set up for all of you. All right, so this session on towards open and standardized imaging data. People are still showing up. I'm going to start though, and we'll see where we go. I realized as I was creating the slides that maybe I should have gone for a simpler title and just called this Bioimage Formats 101. Part of that's so that we make sure we take everyone who's showing up along with us. So if they've not done significant work with image file formats before. The other part of this, though, maybe for those of you who have been doing this longer, and I see some names that I definitely recognize, is that there's not a way we can think about maybe restarting our world. Can we go back to the beginning and do things in a different way? And so maybe by the end, we can talk about how is it that we get to this kind of new future. So briefly, what will be the goal for the next 30 minutes? So I'll try to keep myself to that to focus on more on your questions. Is I will give you lots of links, and you can go ahead and scan the QR code or follow the link that is in the chat. That will give you the PDF of the slide so that you can click all of the links because I will not be able to cover everything. And there's lots of resources that you should follow. And if you ever need the DOI for the Zenodo, it's at the bottom on all of the slides. And everything CC by, so feel free to reuse it. Okay, I'll give you some background about myself and a little bit about bioimaging. And then from the webinar text, we have some grand goals that we're supposed to achieve today. So you should all be able to read hundreds of file formats, store metadata in interoperable formats, scale your storage to clouds and clusters, and generally improve data sharing. There's a star on that. We're only going to get so far. I will definitely talk about TIFF and OME-TIFF and bioformats and OME-Zarr. Welcome to talk about the rest of it in the Q&A, but hopefully there's material to get everyone started. But again, I want to get to your questions, so I'll do my best to keep it short. Speaking of which, I forgot to start my clock, and so that's running now. Okay. Was mentioned who I am and that the fact that I'm a senior RDM officer for German bioimaging. If you don't know, German bioimaging is a scientific nonprofit representing the imaging facilities in Germany. At the end of the day, though, I'm really a software engineer. So I build software and infrastructure to try to make things, I assume for most of you, easier. That means I will definitely be showing software examples and pointing to software solutions that I think you would want to use. Since I don't know your level, how much experience you have, I will try to also point you to training resources if you haven't used Python before to get there. So I think everyone can bootstrap into using the tools I'm talking about. And if not, we can work to help you get there. Okay, I'm currently funded by Germany's National Research Data Initiative, NFDI. I'm tasked really with coming up with a standard for bioimaging. But since science is global, doing that at a national level isn't ideal. So we're doing all of this under this umbrella of OME consortium that I've worked on for about 20 years, focused on building this infrastructure and making it possible for all of you to share your data. So we're keeping going. We want more people to get involved. And so if you have ideas or thoughts or would like to help, don't be a stranger. And I'll get rid of my acknowledgements up front because we've been doing this so long. So I was at the University of Dundee for 18 years working on this with various funders. And since then in German bioimaging. And you can imagine that's also very many team members who have helped to build all this software. I definitely can't take credit for all of this. And all of it's a part of the larger ImageSC community. So this is the community that we want to be a part of and grow. So if you click on nothing else, it's probably for you to go to ImageSC. That's where you should be asking your questions. That's where you can find solutions. That's probably the most important thing. So remember that if you're not already there, it's a good place to find software. Okay, so on the background side of things, I'll tell you how I got started with all of this. It's probably a pretty similar story to how many of you got involved in this. I'll tell you about the part of FAIR we're talking about today. It's not the whole story. So on the first webinar, Mike Smith gave an introduction to all of FAIR. If you haven't watched it, so for people in the recording, they can stop and they can go watch it. For all of you, if you haven't seen it, then I suggest watching it afterwards and talk a little bit about what is and is not an image, at least in my definition. Okay, so I began my time in bioimaging with Omero. I was working on the server, so building up this research data management application to deal with the imaging problems that many of you probably have. Fundamentally, it lets people collaborate on data publication. So here is a simple time-lapse experiments that are stored, or you can have high content screening data that's stored. You can have whole slide imaging, MRI, medical data. The list kind of goes on and on. And in this server, we want to make it possible to have a single API for people to access all these diverse types of data, have a security system, be able to annotate their data, create figures from their data. And fundamentally, though, it's a software solution that anyone can install and have on their own. So there are various OMEROs around the world today. I worked with the team in Dundee to build the image data resource. So an international version of OMERO that people can submit their data to for free. So you can look at that as well. But at the end of the day, so we take submissions of data that can be problematic, probably like, again, many of the problems that you're dealing with, and now have 14 million images. So I'll show you a couple of examples of the types of things we've dealt with, and then we'll get into the details of file formats. So what led me to build OMERO originally was something called the MitoCheck project. It was a collaboration between my lab at the German Cancer Research Center and EMBL and a few other groups. And fundamentally, they were knocking out every gene in the genome and then seeing what happened with mitosis, and took a large number of videos. And that led up to 25 terabytes of data, which today, is what it is. It's still not easy to work with, but I can tell you in the early 2000s, it was a nightmare. And we fundamentally needed to start building the kind of software that I'm talking about today. A few years later down the road, we received this zebrafish image. So it's single 2D plane. It just happens to be a very, very large 2D plane. So it's over 900,000 pixels wide and over 300,000 pixels tall. And at least according to Wikipedia, it was the largest image on the internet for a period of time. And we were hosting this for the Journal of Cell Biology, and it required an entire OMERO server, an entire physical server in New York on its own just to host this data at that time. It then went viral and was being clicked on 3,000 times a second, and it took several people day and night for several days to keep the whole server running. And so that's the type of problem that I would like to get behind us. Like, no one should have to spend their life doing that kind of thing. Similar problem moving into 3D. So from the team at Genelia, the Keller lab, submitted mouse embryo data. So 5 terabyte for one 3D volume lets you track every cell in 3D during development. And they needed to develop their own file format just to be able to do this processing. And so, welcome to ask questions about these types of things. I assume you have these stories too. And so as a community, what is it we can do to kind of move beyond these problems? And so the piece of FAIR that we're going to focus on today is really thinking about how we go from files to images. So in Mike's presentation, he talked about research data often, in most people's minds, comes down to files on disk, right? And there are different types of files, and you can have surveys and you can have text files and spreadsheets. And of course, we have things like TIFF and whatnot. But how do you go from having those files on disk to having images? And I'm preparing for this, I went back and found some very old slides to show you how long we've been dealing with this. You can have a single image, a single file that maps to a single image. That's kind of like what most people would expect, I think, when they start to get into data management. But you can also have single files that map to mini files, like this Apereo SVS. So it's pretty common in whole slide imaging to have multiple images in the same data structure. But you can also have a large number of files that map to either one file or mini files. And so fundamentally, we're left at the end of the day wondering, so as someone who takes submissions, like in the IDR or an OMERO system that has to do all this automatically, with fighting with this mapping between the two. And it needs to be standardized, and there needs to be a way that we can all as a community represent those things. And that's about as far as I'll go into the depth of some of these topics. And here I'll start pointing at the training resources and give you a little bit more background. I'll point to the NuBias training resources. Unfortunately, I don't know the names of everyone who's working on it. I tend to talk to Christian Tischler from EMBL about this the most. NuBias, if you don't know what it is, was the Network of European Bioimage Analysts. So it was a funded project for 5 years where we got together twice a year at very lovely locations and held workshops and developed material on expanding the bioimage analysis community. It was good times. Since the Global Bioimage Analyst Society has developed, it's another funded project hosted at German Bioimaging, and new hackathons are taking place, new workshops. And so if you're looking for a place to get involved and go visit people, that might be a good place to do it. Even more fundamental would be the carpentries. If you're still looking for material, for example, there are the data carpentries image processing lesson, which will tell you even more kind of the basic entry into using Python libraries for image analysis. And if you also don't know how to use Python and you want to get started there, go all the way back to the software carpentries. There are lessons even for getting started with Python and learning Git. There is a pathway to learning how to get involved in this community. I guess I'm trying to say that over and over again, right? Okay, finally, what is and what is not an image from my point of view? So that's kind of the basis of what we're starting. And fundamentally, so in the second webinar, Katrina and Stefan talked about, they showed images from the Trick project. They were fundamentally, the type of image you would take with a camera or even with your cell phone. And that's at one end of the spectrum of what I think we're talking about today. And then from there, heterogeneity takes over. There are all kinds of modalities, and then moving on from using photons to using electrons to using X-rays, multiple lasers, basically anything's possible. And so what my role has been with the OME project for many years is trying to define a central model that we can use for bringing people together so that we can at least have a basis for having these conversations. And at the basis of that is a multidimensional structure, which we call an image, right? The higher dimensional dense thing that certainly has at least can have the 3 physical dimensions, can have multiple colors, can have movies, so it can be time lapse, or if you're using film data, it can have multiple time accesses, and you can have various combinations of these things. And that's just for the image. And of course, you can have even more complex acquisitions that build up for high context screening or single cell tissue, where you have different modalities that you're overlaying. And doing all of this with TIFF is difficult, even though that's what happens most of the time. So if you don't know what TIFF is, a very quick introduction. Fundamentally, TIFF is a little bit like a book. You have a page that is the header of your TIFF, and it tells you what the book's about. You have a table of contents that tells you where to go in the book to find an image. And then you have one or more images in the book that can be broken down into tiles or into strips of information that can be compressed. And that's kind of it. It's coming from a very non-scientific background. And so that's the full model of what TIFF gets you. And what that means is that when you have a TIFF on disk, so you know what it is, but if you ask a computer what it is, at most, it's either a single image or it's a list of images. It's not necessarily a 3D stack that you have acquired or a time lapse that you've acquired. Fundamentally, a computer doesn't know what your one TIFF is. And even if you have really good file names that everyone would understand, that doesn't turn it into a multidimensional image, right? So you've named your stack and you have a time point and you've put metadata into the file. That still doesn't make it a stack. Something else has to come along and turn this thing into a stack for you. And so what you might want to do if you're wondering, if you have a bunch of TIFFs around, if you've done this, as many of us have, you probably want to use something like TIFF file, this library that's linked down here. And I'm looking at a particular image from the OME repository called Caspian TIFF. If you open it in TIFF file, you can see that it's a pixel, it's 279 by 220 pixels, and there are 3 channels, and they're all stored in a single page. So this is kind of the simplest example, right, that you can have. It's the low end of the bar. The thing is, though, if you start pointing this at your data, and I suggest you actually do that, go and try to play around with it, it will realize, depending on how you've grouped things, if you've done it in the right way, whether you have an OME-TIFF, which we'll talk about in just a minute, or something like an image J-TIFF or a GeoTIFF or an ND-TIFF, and there are all these types of TIFF stacks that have evolved over the decades, certainly decades. I was going to say centuries, but just the decades. And TIFF file is a great place to know that, to tie it all together. It knows, it has the logic of how to do that. And actually the developer of TIFF file, Christoph Golke, is probably one of the people in the world who has the most knowledge of doing how to do that. So it's a great place to start. And this happens all the time. So most of the data in the IDR is TIFF-based. Most of the file formats that exist in bioimaging are fundamentally TIFF-based, so it's not going away anytime soon. But the specification belongs to Adobe. And in various attempts over the years to engage with them to try to expand the specification, we failed. You can imagine our community is not big enough or worth enough money for that to happen. So at the end of the day, TIFF itself doesn't have a scientific model. So it's this very simple book data structure that we're talking about. And it also has limitations as you start to scale. As your images get larger in any two physical dimensions, or as you have more and more TIFFs in a single book, it gets harder and harder to access those just because the book gets larger. And so what's happened is there have been a large number of file formats that have been developed by companies that we call proprietary file formats, with which we mean the specification of the formats isn't open to the community. It's not something we can get involved with. And there are companies that are very open to working with the community. They publish their specifications. They build open source software that we can use to access them. And then there's everything you can imagine on the other end of the spectrum. But one thing we did early 2000s, around the same time that we started building Omero, was to say we're also going to develop an open source, open community specification, OME-TIFF, so that we could have input into what was happening. And so that's the format that we would, as of today, the status quo, say, this is the best we can do at representing these complex representations. And then what we'll talk about in the second half is what's the next generation of representing these structures. And so TIFF, this is kind of a more complicated representation of a TIFF, but fundamentally it has a place in its metadata called the image description. There's exactly one of them. And so only one community can own it. So you can't have like a mixture of specifications from different communities. And so what we've done with OME-TIFF is to take a block of XML representing the image parameters that you would expect in microscopy, represent those as XML, put them in the image description. And with that, you've got something that's this higher dimensional structure, right? That's the basis of the specification. And so something like TIFF file is reading that XML to figure out what your data looks like. And so very briefly, again, I can share a link to these Python files if anyone really wants to look at them. There's another data sample that's in our repository. You can download it. It's, I think, tens of megabytes. It's pretty easy to work with. And when you open it, you see that it's, again, a fairly small image, 439 by 167 pixels, but there are 5 channels in it and 7 time points. So it's a very small time lapse that we use for testing things. And you can see that there are 35 pages in this book. So it's starting to get more complex. We've put them all in one TIFF, so it's not a TIFF stack, but fundamentally it's part of this kind of 5-dimensional world of images. And there's another library called OME-Types, which helps you can pull out that XML block out of the metadata, and you can have objects that you can start to inspect to say, okay, I want to understand what's going on in this study. Please show it to me, in this case, in Python. And that's something you can and probably should try with your data to see, do these libraries understand what you're trying to communicate with your data? There's another library that I won't go into in depth called bioio. If you're really going to start trying to access many different file types, so not just TIFFs, but many different file types in Python, you should probably try it out, right? OME-Types and TIFF file. So TIFF file is just for TIFF, and OME model is only for reading OME XML, or OME-Types is. But if you want to go beyond that in Python, probably look into bioio, but that's a little bit too much to get into today. And there are examples of using bioio, it's kind of hard to say, across the training resources. So every one of the examples in the training resources will show you either how to do something in ImageJ or how to do something in bioio. So it's a good place to start. And that includes many, many more details of working with OME-TIFF than I'll get into today. And so that brings us to bioformats, because fundamentally, we need something in our community that will, like TIFF file, tie all of the different TIFF formats together, that will tie all of our formats together. So part of that can be using the libraries from companies directly. So bioio, for example, has any company that has provided an API that we can use for accessing their data, bioio will wrap it, And then for everything else where the company hasn't provided us a library, it defers to bioformats. And so bioformats becomes kind of this like standard way of representing all the different file formats. It's also shipped inherently in ImageJ. So if you're working with ImageJ and opening files that are complex, quite possibly you're using bioformats even without knowing it. And what it does is it sits in the middle between all of these mini file formats. It's some 160 plus file formats. I didn't get a updated number. And it maps all the binary data and the metadata it can into the common model, and all applications are welcome to use it. And then there's a bunch of other metadata that we don't necessarily know what to do with. We can't parse. We try to show it to end users and we kind of just print it out so that they can understand what's going on. But at the end of the day, this is still one of the biggest problems we have, is that we don't know precisely what all of the proprietary file formats are trying to communicate. And that might also be something we want to talk about before the end of the webinar. There's a list available. So if you're wondering if your data file format is supported, feel free to go click on that. I tried to get a screenshot that showed all of them. It's not particularly useful. And it also reminds me of a question that came up during Mike's webinar, which was, what happens when the commercial software that created your image or that you worked with your image with no longer supports it, right? There's a archival question here, is what happens over time? And so just tell you a story. So what we try to do is very much to support all the old formats, basically any format that we've ever supported. There are probably a very few number of exceptions. So every day we test bioformats across terabytes of data that's been submitted by the community. And that includes the old versions and much newer versions. And we've heard from at least one company that they do not do that. They test exactly 2 versions of their format, and that's it. So to some degree, our community has deferred the responsibility for the long-term support of our data types to bioformats. But I can tell you that's a burden that's very hard to support. And so again, looking towards this new possible future, this new restart of bioimaging, and how can we get there? Just a few more ways you can possibly start using bioformats if you're interested. So if you click on this link, you will get a zip that gets downloaded. And if you have Java installed, then you will have some command line tools that you can use. Show-inf is one of them, and we will probably ask you to use it if you ever tell us that you're having problems with your data. So it will print out something like this to you, which looks like gibberish. I think if you could see it closer, you could read it. It's basically saying, here's what I think your data looks like. Here's the dimensionality. Here's your pixel type. Here's all the basic information. And so you'll know whether or not bioformats is interpreting your data correctly. It will also print you out a little GUI, which isn't particularly helpful, but it does let you know, are the pixels being read or is something missing? And like I said, we will probably ask you to do this if you're having a problem that we can't solve. The way that works is if you're having a problem like that, is we will very much encourage you to go to ImageSC. You can follow this link, report a problem. And if we can't fix the problem just based on your description, we'll probably ask you to submit the data. And the data will go to Zenodo and you'll give it a license. And then that will become part of our daily testing process, right? So this is what happens really on a daily basis. And we try to answer anything you post here within 1 business day. So a lot of effort goes into making sure that the community doesn't lose access to their data. But as I said, that's getting harder and harder. So one of the things we're encouraging people to do more is to actually go ahead and convert their data into a different format. So here showing how it's a very simple example. There's a command called bfconvert. You take a different input file format and you convert it to OME-TIFF. The screenshots look identical, so it's not telling you much, but that's what you want. You want the input and the output to be as close as possible with no loss of information, right? And we're getting ever closer, and hopefully we can get closer, even closer with OME-Zarr. We'll look at that in just a second. So one last point when it comes to all of this. So the reason to do this conversion, so one of the big drivers is the fact that, so you know how your data is working. You've got these proprietary file formats, you've got your pipelines, they work for you, you've got your tools, that's fine. If you submit that data to one of the repositories, the users are left downloading that data, right? And then they need to understand your pipeline. They've got to install bioformats. They've got to figure out whatever it was that worked in your particular scenario. And that's going to lead to problems of scale. So fundamentally, this will keep people from using your data if your goal is to share it. And so the question we're asking is really, how do we go about developing a new format, a specification, a community way of doing this, such that you can leave the data in the repositories, you can access it from all of these clients, and you can do that without the need for the translation and then without the need to download everything. Okay. Halfway summary. Quick overview. TIFFs are a list of tiled 2D images. XML, OME-XML helps us tie those together, at least in our case. And then we put that into OME-TIFF to build up these more complex images. Bioformats can read all of those things in the 160 file formats. Other tools can as well, like bio.io and TIFF file. But we still don't have a standard, and we've got a download problem. So that's where we're going to get to. I knew I'd have a problem with my voice at this point, so I put in a break for drinking. If you need something to drink, do that too. I'll mute my it almost matches. Okay. Let's keep going. Reasons for OME-Zarr. So kind of explaining it a different way, the download issue. If people have to wait for 5 terabytes of data, so it says upload, but it's also for download. 5 terabytes of data to download, even 10 gigabytes of data to download, they're going to get bored. And they're probably not going to look at your data, or certainly the percentage that are going to look at your data is going to be reduced. So imagine some magical future, we're not that far away, where they don't have to do that. And they have some kind of Google Maps style access, right? And they see a little bit of data, and if they like it, they can keep reading more data. So that's where we want to get. But because this is an important enough use case, right? There's enough drive in the community in this new fair world, enough interest, that it's also an opportunity for us to define together how we can do that. Can we get beyond kind of the smorgasbord of formats and complications that we all have to deal with, and have a simple way, a unified way of sharing these arrays, essentially nothing more than arrays, remotely with our community. So and how far can you take that? So try to imagine, dream big, right? By the way, all of these images are copyright NumFocus, but they're CC BY. And so you're welcome to use these in your slides. You can go download them here. We developed them with Henning Falk, the artist, for a publication on volume EM a couple of years ago. And they helped to get things across. Having an artist around is a wonderful way to communicate things. So can only suggest doing more of that. And so that brings us really to coming up with a format that you can call it a chunk file format. You can call it a cloud native file format. But fundamentally, we want to move to this new situation. So whereas TIFFs are kind of monolith, or HDF5 are monolithic file formats. So they're large binary sequences. They're opaque. You can't really see into them. They've got a header, this first page of the book that tells you what they're about, and the table of contents. And then that tells you how, where to go in the binary. But fundamentally, it takes sophisticated software for you to then work with that. And so what we're asking here is, can we not break that apart? So as soon as you've got a couple of different TIFFs, so TIFFs weren't made to do this. They're a monolithic file format, but people are already starting to create multiple TIFFs and then kind of put them together. And so as soon as you do that, you can start to build a file format that does this natively, that's built on the concept of saying, we're going to have a well-known name on disk for every chunk of an image. Every pixel belongs to a chunk, and you know exactly how to find each of the chunks, and all of that's compressed binary data. But when you've broken it apart, you can also, for example, then take the metadata, and you can put that into an easier to read file like JSON or YAML. And then you start to get a bunch of benefits. You can write that thing in parallel on a cluster and go from many days of converting your data to many minutes of converting your data. You don't need a server necessarily to access the data. So if you can put it up on S3, then you don't even need a Numero, and I'll show you an example of that. And fundamentally, the name of each of the chunks, if you put it up online, becomes a URL. And so we start to have a very web-like way of working with our data. There are definitely downsides, and we can talk about more of the downsides if you want at the end. It's hard to work with many files at a time. Users don't always understand the fact that the whole directory is their data as opposed to just one of the chunks in it. But we're getting there, and so we'll keep improving all of that situation. But once you have this, once you kind of have this URL layout, the structure of representing your data, what you can do is build very simple web pages. So this is a static GitHub website called the NGFF validator, so the next generation file format validator, which uses that header. So it grabs the JSON from the header information and can tell you about your data. And it knows the size and the layout of the data. It knows as soon as you click on it, it knows where everything is and is ready to start loading chunks, but hasn't done so yet. And then that URL becomes kind of the basis for our standardized access. So here you see a Neuroglancer, but you can also click and go to WebGnosis. There are examples of doing this in Nepari and in Fiji, all based on a single URL that's being accessed, right? And so we're starting to have this goal, this dream, certainly from my side, of saying we don't have to have bioformats in the middle. We can say, we can just send the URL to all of our users and pass it around. And for what it's worth, it all begins with some quite simple agreements. So there's not magic going on here. What allows people to zoom into an image like the zebra fish is having pre-computed resolutions of the image. So basically downsample your image, store them all together as a multi-scale pyramid, and then you can get Google Maps style storage. It's a pretty understandable idea. Many people have developed it at the same time. And what we saw in the community was people are doing it in quite similar ways, just some with slight prefixes to their multi-scale resolution levels. Some were saying the large resolution was the 0. Some were saying the small resolution was 0. And what it took really was just getting the community together and saying, okay, let's build a very small specification that lets us write that down. So it supported everyone's use case, but did it in a more flexible way, in a way that the different clients could understand. And that became the basis for the next generation file format. It's part of the specification that lets us do this. And then from there, many more conversations over the years, right, to work towards a more complex data structure, but hopefully something that's becoming a fair standard. And so this is a representation from the 2023 paper of a single URL representing a whole high content screening plate, where at the highest level, you have a plate that's a terabyte of data. And then following the pink boxes, you zoom in until you get down to a level that's really only a megabyte, right? And so a client can load those megabytes on demand and not need to load everything. And that went into the 2023 paper, bringing together as many authors as we could, saying, this is the direction the community wants to go. And so very much invite you to join that community. Can't imagine how many authors will be on the next paper, but it's coming as we move towards this. That process continues. So these are now happening via RFCs, requests for comments. The current body of work is on image registration. So it'll be to add coordinate transforms to the specification. It's been a while in coming, and I would point you at a YouTube video from John Bakovic from Janelia, and he's really leading this work, and he will explain it so much better than I will. I will just defer you to that for after the webinar. But he will explain why we need this, how it's useful, and how the process goes of adding those specifications to OME-Zarr. And then if you want just help getting started with OME-Zarr, again, I'll point you to the training resources. And there are also other big image file formats that have been documented. If you personally wanted to get started today, I would point you at the NGFF converter from Glencoe Software. So Glencoe is the commercial arm of OME. They license Omero to companies and help to actually really drive the development of bioformats. They've built a drag and drop application that works on Windows and on Mac. And it looks like this, so that once you open the application, you can drag your data onto it. You can hit run conversion. You get an OME-Zarr, and then you can then open that in applications, right? So not really that much different from BF Convert. It's exactly what you would want. It should look the same before and after. The more important thing is that you can take that directory that got generated, put it somewhere online, and we can talk about different places you can put it online. and now you've published your data. Now there are questions of, how would you get a DOI? How would you make that available to the wider community for a 10-year period of time? That's a different question. But in terms of, have you shared your data? Have you made it available? That would be the two steps, right? Do the conversion, upload it, and then you will have far more engagement with your data than you would have if it were just, say, a 5 terabyte download somewhere. And that then brings up various possibilities. So you have the ability, you can make a web page like this, which is our sample page, again, just a static GitHub website. And we've published the zebrafish there. And so you can go and you can actually do the Google Map style zooming. So do feel free to do that. This is using a tool called a viewer called OME-Zarr, but there are many others. And so it really depends on what your needs and your access patterns are, but I guess let us know if you're having issues. You can even do something like this, and I'll zoom a little bit ahead. Christian Schmidt from the NFDI for Bioimage program recorded himself going through that website, or the website I'll show you in just a second, actually, on his phone. So loading hundreds of gigabytes of data. Wow, that's the marketees. Obviously, you're only loading the chunks, the megabytes of data that you need to actually look at a given time on your phone. But from the user's point of view, it's still a URL that is hundreds of gigabytes, if not terabytes, and they're looking at it on their phone. And it's quite a big change from where we were in the beginning. Another possibility that we realized, I guess, last summer, we hosted a challenge. The goal was to get to a petabyte of data in a federated repository. So i.e. everyone brought their own storage, and again, built a very low-cost website on, I'll make this stop. Oh, apologies. On GitHub, and it's accessing all the S3 buckets from people who took part in the community. Again, if that's something you need to do is share large-scale data, maybe an opportunity that you could take a look at. And I think the good folks from Bioimage Archive also are seeing the same benefits. I'd point you at Matthew Hartley's presentation, also from the OME 2025 meeting recently on YouTube, talking about not only the ability to use OME-Zarr for publishing the data that has gone into the Bioimage Archive that I think Stefan talked about a little bit in the second webinar, but even taking it as the input format, because they have the same issue that as data comes in, like with the IDR, they must interpret it. So if we can have it in the common specification, then there'll be less loss of information as we start to publish our data in the archive. Okay, I'll stop now, slightly over time. Take homes for a fair future. So again, some kind of dream of being able to easily share things. If you're unsure of where to start, you probably want to try to at least point bioformats at your data. Or if you're in Python, try bio.io, and just see what they think your data looks like, right? And you probably want to try at least one other tool. So not necessarily bioformats and bio.io, it can be another one, but fair comes down to the ability of software to be able to auto detect what you're doing with your data and be able to work with it in a consistent way. And so if two tools see your data differently, there's probably a problem. And a lot of that comes down to files like TIFF or file types like TIFF and HDF5 not being inherently for scientific images. They're not going away. We will keep using them, but we do need to build these specifications on top of them so that we can work together. If your data works in OME-TIFF, especially for your access patterns, go for it. There are a large number of tools that support it. And so if that's what you need, feel free. But if you start to run into problems of remote access, or you need new forms of kind of next generation structure, so you need the transforms, you need more complex things that aren't in OME-TIFF, you probably want to try out OME-Zarr and get involved with us to define the community standard. And if you notice yourself either defining a new file format or new metadata structures, get in touch on ImageSC. Let us talk about it, because it might be that you can just be part of the growing community and not everyone in silos. So I'll try our best to keep that from happening. I think with that, I'm done with slides. I will mute for a second and see if there's anything we need to go over, and I'll start reading questions.
Yes, thank you so much, Josh. It was a great presentation. So just before we move on to the question, this is a brief reminder This webinar is part of a larger webinar series. So here you have the list of webinars. Some already happened, so there are recording available on our website. And tomorrow in the email you will receive, there will be a link to the webinar series page so you can catch up with everything you've missed or register for future webinars. So without talking about this anymore, we can move on to the questions because we have quite a few interesting questions in the Q&A. So I see two questions that are kind of related to each other, so I will try just to rephrase it for the audience. So someone is asking, let's say I convert my data, my raw imaging data, and then I do not want to keep the original version, the proprietary file. So I delete it, but at some point I need to switch back. So they want to know if and how they can do it. And another person is asking a related question, that is, how can I be convinced that this is a safe practice, that I'm not losing any information from the initial image once I move it to the OME format?
Yeah, they're both great questions. And I think the short answer is we're not there yet. You're okay? What it's going to take to get there will be a representation and probably an agreement from the companies that they can export their metadata in an open format completely. So what we very much would like to achieve is the statement, anything that the original file format doesn't export to us doesn't exist for the user. And so that's going to take some more time. That's essentially, let's say getting to the point where we are today with OME-Zarr, so for the binary data. Like, I'm quite convinced that when we go through these conversion processes, we're not losing binary data, right? I think that's fairly safe. And so let's say it took us, 6-8 years to get to that point. I think, unfortunately, we have a body of time. I hope it's shorter to get there with metadata. But talking to the companies, and I think all of you have a loud voice when talking to the companies, especially when purchasing the microscopes, to say, you want something like this. You want a way to export your proprietary file formats completely to OME-TIFF and OME-Zarr. And that's going to take investigation and looking at what comes out and making sure that you can do the things you want to do. So A, the downstream analysis, but then also B, getting back to Tina's question of taking the converted data and taking it back to the microscope, loading it and going, oh yes, it looks exactly like the original file format did. So that's going to take many of us experimenting with this. But it is what needs to happen if we're going to move towards a common format.
Okay, so we then have another question about related. So how fast is the conversion? So it's the same person asking different questions, so I'm going to ask them all at once. So how fast is the conversion? And do you have experience on file size of raw versus OME-Zarr file format? And if there is someone that is in charge of maintaining the conversion in the sense of adapting it, if there are modifications from companies?
So I'm not quite sure.
Yes.
Okay, so I'll start with the adaptation. I'm not quite sure what the question means with the modifications from the companies. So someone, maybe you can re-ask that part of the question while I answer the other ones. In converting, I think especially, well, since we're generating the multi-resolutions, I would almost always expect there to be some increase in size, unless the input format also had a multi-resolution that we can just copy over, right? There's a best case conversion scenario where it's basically the same size. For most file formats, there will be an increase in size that's not too bad. And then there are still some cases that we're working on, especially where the input file format has lossy compression. So I'm thinking of like whole slide imaging with, say, NDPIs. There's still a situation where we assume everything that's coming is with lossless compression, and therefore it gets much larger. And so that's something that the community is actively working on, is trying to go, okay, well, let's then just accept the fact that there's lossy compression involved and keep the lossy compression in the output format. And so certainly working on that. And if that's something someone's interested in, feel free to get in touch.
So if the person can just rephrase the initial part of the question, we can come back to it after. And then we have a question about, do you have a vision to using the data access for AI agent interpretations?
I don't completely understand this one. I think my short take on this is there are quite a number of people in the community, in the Zarr community, not necessarily in the OME-Zarr community, that are actively using Zarr for loading in data, binary data into, say, models. And I think that's what you're asking, but feel free to re-ask. But if someone's interested, again, I can point to, and we can do this on ImageSC. You should always do everything on ImageSC. Many examples of how you can go about loading data into your model, if that's the goal, right?
The next question is the additional or multiple levels of resolution not increasing the overall size on disk of the format?
It's definitely doing that. And this is a trade-off. You can choose, of course. So I think I mentioned this, but to make it even more clear, everything in the specification, so everything, all these different numbers I kind of showed about how big are your chunks, how many chunks do you have, how many sub-resolutions you have, they're all choices, right? And so you could choose to have no sub-resolutions, right? Only have the highest resolution data to not have the additional size on disk. The downside will be applications that then go to your data and go, well, I want to view this, are now stuck downloading it, right? It's a give and a take. And so to the extent, and there's no simple answer, I think we'll have maybe best practices, certainly some suggestions, minimally have a very small version and the big version, or, you can choose how much you downsample. And so, maybe test it out and try it with your users. If they're expecting more so that they can, cleanly zoom into something, it's probably worth I think something like 30% increase in size to give them a nice experience, if you want the data used. If you're doing all this strictly for archival purposes and no one's going to be accessing it, then it's maybe a very different situation. So someone was asking, sorry, do you want to do it?
No, it's just because the person that before asked about the company modifications on the file wrote down a more detailed, so I would just take this one so we conclude with the initial question. So it was saying that it was experiencing that if the microscope acquisition software change, because maybe there is a new release from the company, then the metadata of the images entirely change, and was experiencing, for instance, some Python libraries were not functioning anymore. So
yeah, okay. I understand. And this happens a lot, and it happens, so that's a fairly, that's a whole color change, whatever the color change means. There's also the same thing happening on ImageSC, like even this morning between different versions, a new version of the software came out, the same software, just a new version number. So you asked originally, who's responsible for keeping up with that? And I think at the moment, unfortunately, it's still us. Well, some companies provide their own SDKs, but then you need to know which version of the SDK to use. For bioformats, based formats, it's our responsibility to know those things and use the data that you give us to test. But we would like that to change. And that really comes down to this: can they export all of their metadata? So we will be driving this process. And again, I will very much keep encouraging the community to tell the companies this is what you want. So as long as the company can tell us why there's a difference between blue and black, they can, when they export it, if I can see a difference between the two things, because it's been communicated in a capital letter fair way, then I can build software to deal with that, right? But it has to be expressed. We have to have a language to talk about these things that we don't have yet.
Thank you. So the next question is, how can I load the OME-Zarr file in Omero? Because apparently this person tried to do it, but was very slow in the scanning phase. So
yeah, there are a couple of different ways. I would say Insight's not the place to start. We can probably get it to work for you. And so again, feel free to speak up on ImageSC. Worst case, try the command line. And then Glencoe is working on a a different way. So it's interesting. So everything I kind of told you, it's about thinking about OME-Zarr as a new way of working with data. And so Insight, Omero Insight, is trying to import it as if it's regular data, the old school common data. And so what we really need is a new way of getting data into Omero as well. And so we're working on that at the moment. And what that might look like, for example, is just telling Omero, okay, there's some data over there in S3, and you don't even actually have to transmit it to Omero. And that's being used currently at a number of pharmaceutical companies. And if you're interested in trying that out, I guess please get in touch.
Thank you. And the next question is, does OME-Zarr support sparse array formats or layers?
So, I mean, this is really largely a Zarr question. And so we have to go all the way down to Zarr, and not really yet. There are certainly people who are thinking about it. There are things you can do in terms of storing individual one-dimensional arrays. You can act like you have a sparse array. It's still not optimal. There's definitely work to be done. Probably the closest or the most actively investigated area is storing mesh files in OME-Zarr. So those are fundamentally stored in a much more sparse format. And so I think we're getting there, but knowing that people are interested is already a good start. So I guess keep banging the drum and we'll get there eventually.
Thank you. The next question is about metadata. It's a little bit a more structured question, but if I understand it correctly, so someone is saying the microscope metadata might not be sufficient. For instance, there may not be information about which channel represents what biological structure. So do you recommend including those experimental details as sample metadata even sample metadata in the image metadata when storing the image online?
Yeah, I'm very much in favor. I think it's actually a fairly similar story to working together with the companies, that various groups have ways of representing the metadata in their own way. And so certainly it's a good starting point to just find a place to put it in the file format, so in the OME-Zarr, and save it, send it to us. But that is human readable, and what we need to get to is machine readable. And so we will need to agree, we will need to have the language for groups like RIMBY and Bioimage Archive, and maybe particular, say, marine communities or the volume EM community, a way for them to write down their data and store it in a machine actionable way. But we should definitely get there. Agree completely.
Thank you. So the next question is, are these converter portals NGFF reliable and free from software license, etc.?
So the converter, so the NGFF converter, so it's a software application, not a portal. Is it free from software licenses? No, but it has an open source software license, if that's what you mean. Anything that is based on bioformats is under the GPL, because to support bioformats over the years, that was the maintenance structure that we chose. But you can certainly have converters that are GPL free or otherwise licensed, and there are definitely examples of those out there. BioIO can do a lot of it without the GPL, if that's your concern.
The next question is about storing 3D data. So can you do this in OME-Zarr chunks?
So definitely, and the deeper part of this question is sometimes you want different chunkings. Sometimes you want a 3D chunk, and sometimes you want a more tiled-based chunk, and it depends on your application. And so there are examples of people coming up with copies of the data set with each of those chunking strategies. And it depends on your use case. If it's, if the cost versus time relationship is worth it to you, maybe chunk it both ways and then and provide that to your end user.
Thank you. Someone is asking if companies are given the option to export images in the OME format. And I may add, if this is not happening yet, if you envision this to happen in the future.
So There are a number of companies, over a dozen. I took that out of the slides for time reasons. There's a page on the OME-TIFF documentation where we list people who have added support for exporting OME-TIFF to their software and have told us about it, right? So we don't necessarily know everyone, but there's over a dozen different companies provide OME-TIFF export to varying degrees of validation. So it's not always true that when you get one from the company that it will validate. There are some companies that are starting to talk about exporting to OME-Zarr, but it's very early days. So we end up providing the tools to do most of that. In the spatial omics space, so there's another format called spatial data that's built on top of OME-Zarr. And I think there some of the companies might be the first to adopt it because their file formats are very much a mix of JPEGs and PNGs, and they don't have their own file formats yet. They have a conglomeration. So it might be easier for them to migrate to using OME-Zarr.
Thank you. We still have 3 questions in a couple of minutes, so hopefully we can take all of them. So someone is asking, does OME have a way to lobby companies to be more open as a group? Or is it still on individual customers who may be buying a new microscope to lean in before purchase?
Thanks, Terrell. I know what you're getting at. It's a great question. At the moment, it's much more the latter. So it's sending as many customers as possible. But yeah, the community should, and so maybe that's something we'll come asking for soon, is find a way to organize that layer of being able to say that we can lobby with one voice. So it'd be great to get there.
Thank you. Then someone else is asking about different file format that may have more metadata as file attachment, and if there is a plan to include things like this on OME-Zarr. So they're mentioning CZI files.
So not necessarily concrete plans, Mustafa, but we're getting there. So I think this comes down to doing the reverse, not raising your voice to the companies, but telling us what's the most critical for your use cases. And we have a bit of a roadmap, and that roadmap will be published towards OME-Zarr 1.0 soon. And so if you see something that's missing on the roadmap and you're like, I really need this to get something done, I guess let us know. But as a community, we will just keep adding things to the specification.
Thank you. So technically it's time, but if you can stay a couple minutes more, we can finish the questions.
Yeah, we can make it through.
Thank you. So we have a question for image processing and analysis. Do we need specific components or libraries that support the Zarr format, or Dask is absolutely necessary?
So Dask is definitely not necessary. For anyone who doesn't know, Dask is useful for parallel processing. So it kind of wraps the Zarr Python library. So it's a way to access it. You definitely need something that speaks the Zarr format. I guess that's always true, right? And so there's a long list of implementations on the Zarr webpage, and any of those would be fine for doing kind of the downstream processing. You might need to do a little bit of manipulation on the metadata to figure out what it is you want to access. But at the end of the day, the underlying format is just Zarr, so any of those libraries work.
Great. So the next question is the format allowing for recording annotations or ontology?
So there's nothing in the OME-Zarr, so the NGFF specification yet. That's why it's much more focused on the binary data, and then we have this new project of the metadata. So there are places that we put this type of metadata in OME-XML, and since you can put OME-XML into OME-Zarr, like we do with the TIFF, we can give you a place to put it today, but I agree long term we need a better place to put it, and it will become more and more an issue as we try to extract all the metadata from the companies.
Thank you. And I think the last 2 questions are actually interesting to conclude the webinar, because one person is asking, how do you determine the optimal chunk size for different bioimaging datasets when creating the OME-Zarr files, and what trade-off should a researcher consider? So it's a more technical question. While someone else is asking, how long until these tools are accessible to and usable by non-expert end user without a detailed understanding of all the file structures, chunk size, so user-friendly, let's say, for everybody?
Okay, so the 2 ends of the spectrum, nice. Yeah. So we don't yet have a tool or like a web page that says this is precisely how you decide your chunk size. really you need to benchmark, or you need to have a feeling for this is what my users are doing. So certainly in the connectomic space, I think there's a paper from the Scalable Minds team many years ago saying they would suggest chunk sizes of 32 by 32 by 32 for connectomics, per modality. Like, we know we use our data this way, and therefore here's the chunk size we suggest. Recently, for example, they updated that because processing, computers change, Moore's law. And so I think now they're looking towards 64 by 64 by 64. And so I think maybe we need to keep this in mind as something we as a community offer as advice. And so what web page would you go to figure this out? And if you know where to go, thank you, Terrell. Yes, so there will need to be some kind of law that helps us guide our users in the right direction. So speaking of users at the other extreme, I think, so I was asked after giving a presentation like this by a senior PI, Josh, do I need to understand everything you just said? And the thing is, not necessarily. So obviously this webinar is about telling you the details and giving you what you need to kind of communicate this to the rest of the community. A lot of what I showed would be completely in the background for a generic user, i.e., especially all the web tools. You can take the URLs and you can just send users to a URL and they can look at OME-Zarrs with having zero idea about the chunk size. It's getting there with Fiji and Apari. At the moment, you have to install extra plugins and you have to do things just because of how, the complexity of working on the desktop. But I think we can get there. For people who are generating data, they're the ones who need to make these choices about their chunk size. What is it they want people to do with their data? And they will need to understand these things. We can provide tools to make it easier, right? Maybe we don't even call them chunks. Maybe there's some other knob that the user turns to make these things happen. But choices need to be made, and who's making them, right? And I think we will come back to that probably always moving forward.